let's say we want to compute 2 to the power of 1,234 modulo 789. Now, direct computation is very expensive if you just want to actually compute this huge number and then divide it by 789 and see what remainder you get. And even for a computer, this might be a struggle. And if not, we can always increase this. So we're going to see a technique that can make this much more efficient, right? So the idea for that is something called, so this is going to be called fast modular exponentiation. And what we're going to do is something called repeated squaring. So the key idea is to write the exponent. So this exponent that we're interested, this 1,234, you can write it as a sum of powers of 2, right? So this 1,234, you can write it as 1,024 plus 128 plus 64 plus 16 plus 2. And so the idea then is that if you write it in this way, then you only need to look at power. So you're sort of writing 2 to the power of this can be written as 2 to the power of this sum. And so you just need to multiply those, and you can look at it as powers of like 2 to the powers of 2, right? And those can be, you can compute them by just squaring them repeatedly, mod 789, and then you combine. So let's see how we can do that. Let me copy this and put it here for reference. Okay, so let's take the powers of 2, mod 789. So you start with 2, then you take the power, you square it, you square that, you square that. Now notice that at some moment you're going to exceed 789, and the trick here is that when you do that, you don't deal with this huge number, you quickly take its modulo. So this will just be like, if you divide this by 789, the remainder will be 49. And now you deal with the 49 instead of dealing with the big number. And so the idea is that if you're always doing things modulo 789, then the largest number that you can potentially get inside of here is 789. And so the largest computation that you will do is 789 squared. So it doesn't matter how big this is, you're never going to go over actually doing 789 squared. So you square this, you get 49. Okay. Now square this, and again, take the modulo 789, you'll get 34, and continue to square. So compute these powers of 2. And again, you never let the number get out of hand. You always take the modulo 789. Okay, now that we have all of them up to 1,024, which is the largest number appearing here, the idea is that when we do, let me put a different color, when we do 2 to the 1,234 here, well, this, we can write it as 2 to the 1,024. And of course, if you sum the exponent, you just multiply. So 2 to the 128 times 2 to the 64 times 2 to the 16 times 2 squared. And now these, you can go in your list that you computed here and get them. So the 124 is going to be 286 times 559 times 367 times 49 times 4. And the trick here again is that you never let numbers get out of hand. So when you multiply these two, you don't like multiply this times this, you get some huge number and then you multiply by this. You multiply this by this and you take it modulo 789, so that you never again go over that squared in terms of how big things are. So if you do that, here you will get 481 modulo 789. And so this solves the problem. So what is 2 to the power of 1234 modulo 789? It'll be 481. And you can do this with like a regular calculator, because the numbers are not going to go, none of the numbers are going to become too huge, right? If you take a regular calculator and try to do this, it's not going to work, right? And then divide by 789. So all of this you can do with a regular calculator. So let's talk about that more precisely, like what are some of the advantages of modular exponentiation, of this idea. So the first one, like we saw, is that it's fast. So to compute, or at least faster than doing it in the naive way, the idea is that to compute that, you do at most 2 log b multiplications mod n, right? And so this is much better than multiplying a total of b times, right? It goes like a log of b instead of times b. So it's logarithmic instead of like linear in b. And second, the numbers stay small. You never go over n squared. You never go over this 789 squared, essentially, right? Because every time, the biggest number that can happen here is that, and when you do that, you already very quickly go and take the mod. So you never deal with numbers that are larger than n squared. And so if your calculator is, which is always the case, is limited in the size that it can work with, the limit here is just going to be this mod here, not this part. The limit will just be this number over here. So as long as this is like a reasonable number, you can actually compute this can be quite big, and you can actually compute stuff. As an example, let's say that you had numbers that were like of size 100 digits, then a direct computation of this would result in a number with 10 to the 100 digits. And so this is a number that you're not able to store. This number is larger than the number of particles in the universe. If every particle in the universe was storing a digit, you wouldn't be able to store this number here. So this is completely impractical, right? But if you do what we just talked about, actually it would take you like less than 700 steps, and all the numbers would have up to 200 digits, you know? So this is something that you can deal with. You can work with numbers with 200 digits in computers, right? But this is just impossible.